The dream of building a city on Mars has hit a massive roadblock, and it's not about rocket power, it's a strict legal restriction. While everyone is focused on Starship launches, a quiet conflict in space law is deciding exactly who gets to touch Martian soil first. We are reaching the point where international treaties are clashing with our multi-planetary goals, forcing a major shift in the mission plan. The rule is simple: to protect the scientific purity of the red planet, humans can't be the first ones to land on the surface. This isn't just about playing it safe. It's the reality that one human sneeze could permanently ruin our chance of finding alien life. Every breath an astronaut takes releases Earth microbes, making humans a massive biological risk to a pristine planet. Because of this strict rule, engineers have created a radical but necessary workaround, sending an army of advanced robots first. By the end of this video, you'll see why the first true Martian base will be built entirely out of silicon and stainless steel. We aren't giving up on human exploration. We are just letting robotic automation build a legally safe foundation for us. The Outer Space Treaty isn't just a suggestion, it's a strict law against contaminating other worlds. If human bacteria survive the trip to Mars, we might accidentally wipe out alien life before we even discover it. That kind of biological disaster would trigger an ethical crisis and immediately shut down all colonization. This is the true Mars colony ban, a very real legal risk that no space agency can afford to ignore. The consequences of cross-contamination are permanent, meaning humans are currently a legal liability. We only get one chance to explore the red planet in its pure, untouched state, but robots offer a direct and elegant loophole to this massive roadblock. Unlike astronauts, robots can be baked and scrubbed in clean rooms until they are completely sterile. The human body is essentially a walking ecosystem carrying tens of trillions of microscopic hitchhikers. These microbes ride on our skin, live in our clothes, and travel in every single breath we exhale. NASA takes these biological risks so seriously that they've created a strict ranking system for every mission. This is called Planetary Protection, and it's designed to keep Earth's bacteria from hitching a ride into space. The most sensitive missions, like those going to Mars, are placed into Category 4. By sending machines first, we follow the law perfectly without slowing down the mission. Category 4 means the destination is a place where life might actually exist right now. Because of this, any spacecraft landing there must meet the highest levels of sterilization ever engineered. Even a single microbe hiding in a crevice could multiply and contaminate a huge area of the Martian surface. Essentially, if we find life on Mars, we need to be 100% sure it didn't actually come from us. This risk calculus is why every mission is a massive trade-off between human ambition and scientific safety. If a human mission causes a biological leak, it doesn't just ruin one experiment, it ruins the entire planet. That's why the math always points back to one conclusion: send the sterile machines before the messy humans. By letting robots do the initial work, we protect the scientific purity of Mars while still making progress. To understand why machines must lead the way, we have to look at the inputs and outputs of a human versus a robot. A human is a high-maintenance payload that requires a constant, non-stop supply of oxygen, water, and food. Every breath an astronaut takes releases water vapor and carbon dioxide, which must be scrubbed and recycled perfectly. But more importantly, every breath and every movement also releases trillions of microscopic Earth microbes into the environment. A robot, on the other hand, is a low-entropy machine that doesn't breathe, eat, or shed biological cells. We can clean a robot so thoroughly that the probability of it carrying living Earth bacteria is almost zero. This makes the robot a clean, predictable worker that follows the laws of planetary protection without even trying. When we calculate the risk, a human is a walking biological hazard, while a robot is a sterile precision tool. Robots don't need pressurized habitats or complex waste systems, they just need a steady supply of power. This massive difference in biological baggage is what makes the robotic Vanguard the only logical choice for Mars. By using machines as our first wave, we eliminate the biggest variable in the contamination equation: us. This isn't just about safety, it's about efficiency and ensuring our first Martian home is built to a sterile standard. Every robotic movement is recorded, every output is measured, and every risk is calculated down to the last decimal. In the battle of biology versus silicon, the machine wins every time because it simply doesn't carry the risk of life. This predictable robotic performance is exactly what we need to build the foundation for a future human colony. Beyond biology, the real reason robots win the race to Mars comes down to a simple number: mass. In space travel, every extra kilogram of weight costs a fortune in fuel and complexity. When we look at the mass math, humans are the most expensive cargo we could possibly send. To keep a single person alive for a year, you have to pack thousands of kilograms of supplies. Think about it. 5 kilograms of food, water, and oxygen are consumed every single day per person. That adds up to nearly 2 tons of consumables per year, just to keep one human standing. And that doesn't even count the heavy radiation shielding and massive life support machinery required. For a small crew of 4, you're looking at dozens of tons of extra weight, just for survival. Now compare that to the robotic alternative, a machine that only needs power and parts. It can run on simple solar panels, or a small nuclear battery that lasts for decades. It does not need food. It does not need water. It does not need air. It does not need a pressurized, heated habitat. While a high-end robot is heavy, the total mass needed to support it is tiny compared to a human. Mathematically, we can send 10 advanced robots for the same weight cost as one single person. This means 10 times the work, 10 times the discovery, and 0 risk to human life. But the challenges of Mars go far beyond mass and fuel. The journey itself is a literal death trap for humans. Space is filled with high-energy radiation that constantly bombards anything traveling through the void. For a human, this radiation is a silent killer, shredding DNA and causing permanent cellular damage over months of travel. Living tissue just wasn't built to handle the intense cosmic rays found outside of Earth's protective magnetic field. Even with heavy shielding, the risk of radiation sickness and long-term health failure is dangerously high for astronauts. A machine, however, views radiation very differently. It's just another environmental variable to be managed. While a stray particle can flip a bit in a computer chip, we have engineering fixes that humans simply don't have. We use radiation-hardened silicon and triple-redundant systems that can spot and fix errors in milliseconds. If a robot's software glitches due to a radiation strike, we can simply reboot the system and keep moving. You can't reboot human DNA once it's been damaged by a cosmic ray. Robots don't get cancer, they don't suffer from muscle loss, and they don't need a magnetic shield to stay operational. This mechanical endurance allows robots to take the direct, high-exposure routes that would be lethal to a crew. By sending the machines through the fire first, we learn exactly how to protect the humans who will follow later. But surviving the deep space void is only step 1. Once they land, these machines need unprecedented physical dexterity. To understand how a robotic Vanguard will actually construct a base, look at platforms like Tesla's Optimus Gen-3. This isn't a simple rover, it's a precision engineering tool equipped with a highly advanced 25 actuator forearm. This level of articulation allows for the complex manipulation needed to connect power grids and assemble pressurized habitats. But physical capability is useless without autonomy, especially when the Earth-to-Mars communication delay can exceed 20 minutes. Remote control is impossible, so these humanoids must make real-time decisions using onboard inference hardware, like the AI-5 chip. Encased in radiation-hardened shielding, this localized AI allows the unit to learn construction paths and navigate unpredictable terrain. It can even diagnose and physically repair other units without ever waiting for a signal from mission control. This exact fusion of mechanical dexterity and localized autonomy is what makes an early Martian colony mathematically viable. With dexterity and autonomy solved, the timeline for the first wave is already in motion, targeting the 2026 launch window. This first wave will not carry a single human. Instead, it will be a dedicated fleet of robotic forerunners and heavy equipment. Their mission is to land on a pre-selected site and immediately begin the most critical phase: construction. These robots will build a pristine, Class 100 cleanroom habitat to satisfy every legal and biological safety requirement. Working around the clock, they will assemble life support systems, deploy massive solar arrays, and test for local water ice. Only when every system is built, tested, and certified by AI will the first human crews be cleared for departure. By sending machines first, we bypass the legal roadblocks and biological risks that would otherwise keep us grounded for decades. We've learned that through robotic dexterity and localized AI, we can build a functional, sterile home before the first human even leaves Earth. This is the most efficient, data-driven path to becoming a multiplanetary species. If you found this deep dive into space engineering helpful, Make sure to like the video and subscribe to NeuralByte for more high-tech infrastructure updates. Your support helps us continue exploring the frontier of automation and space exploration. You can watch this video on your screen right now to see why Artemis 3 is not going to Moon now.